Hi there, and welcome to our COA Project Presentation. This presentation will be done by myself, Nana Kofi, and my colleague, Chuda Yakung. It is my pleasure to present to you today a topic that has the potential to revolutionize the world of computing, neuromorphic computing. The human brain is a complex organ that processes and stores information in ways that we are still trying to fully understand. However, with the advent of neuromorphic computing, computer scientists and engineers are exploring the fundamental principles of the brain to see whether they can be applied to the design of computer systems. Unlike traditional von Neumann architectures, neuromorphic computing is built on the structure and characteristics of neurons and the complex networks of the brain's neurons, resulting in fully integrated memory and computing, stochastic computation, task-level parallelism, pervasive feedback and recurrence, and continuously adaptive processes commonly associated with learning. These features give neuromorphic computers a strong ability to execute complex computational tasks, saving power and having a smaller footprint.
Programming a neuromorphic computer involves creating a spiking neural network that can be deployed to the neuromorphic computer. Spiking neural networks are a particular type of artificial neural networks in which the function of the neurons in the network is more inspired by biology than other types of artificial neural networks. Algorithmic approaches for neuromorphic computers fall into two broad categories. One, algorithms for training or learning a spiking neural network, which are also known as machine learning algorithms. Examples of these algorithms include spike-based quasi-backpropagation, mapping a pre-trained deep neural network, and reservoir computing. The other type are non-machine learning algorithms, and examples of them include random walks and graph theories. Several large-scale neuromorphic systems have arisen in recent years, taking advantage of the massive transistor resource now available on a single microchip, and in one case, an entire silicon wafer. The technologies, capabilities, and scalable architectures enable neuromorphic capabilities to be extended to support neural network with skills containing millions of neurons and billions of synapses. Some of these systems include the IBM TrueNode chip and the Manchester SpinMaker. As a result of the inherent capabilities of neuromorphic computers, such as real-time capabilities, fast processing power, and low compute power, they are used for performing complex calculations, finding approximate solutions to NP-complete problems, and building autonomous systems such as robots, drones, and wearable technology. However, per the good features of neuromorphic computers, there are still some limitations. The first being the lack of easily accessible and usable software and hardware systems. Although different neuromorphic implementations are available, only a few are made available via restricted cloud access to the computer science community. Secondly, the absence of programming abstracts for neuromorphic implementations make the idea of neuromorphic computing a challenge. This because the programmer must design the SNN for a specific task at the neuron level. That is, the programmer needs to deeply understand the underlying neuroscience principles and the specifics of the neuromorphic hardware architecture to design an effective spiking neural network. And thirdly, as there are standard benchmarks for evaluating algorithms pertaining to CPUs, such as big O notation, there's no standard benchmark for evaluating neuromorphic algorithms. For recommendations, researchers and scientists should develop hardware and software simulators that would be made broadly available to the computer science community. They should also make sure these simulators' performances and scalability must be improved to keep up with the explosion of data and processing needs. Second, in addressing the issue of how best to evaluate neuromorphic algorithms, there should be a diversity of problems drawn from both machine and non-machine learning tasks. This will provide a more thorough evaluation of neuromorphic computers' capabilities and allow researchers to better grasp their strengths and limits across these various tasks. In conclusion, the potential of neuromorphic computers in the future of computer and computational science is only now being realized. There's an enormous opportunity to leverage these systems' inherent computational characteristics, such as real-time capabilities and fast processing power for machine learning and certain non-machine learning computations. Thank you very much.